Hello YouTube. The last time I made a video about sets, I said that a set with n elements has 2 to the power of n subsets, but why? Why does the cardinality of a power set of set S is equal to 2 to the power of the number of elements in that set? How can we prove such a statement? First let's look at the Pascal's triangle. The sum of all the numbers in the first row is 1, which can be written as 2 to the power of 0. The sum of numbers in the second row is 2, which can be written as 2 to the power of 1. The sum of all the number in the third row is 4, which can be written as 2 to the power of 2. You are probably noticing a pattern here. The sum of all numbers in the nth row of the Pascal's triangle is 2 to the power of n, where n is equal to 0 for the first row. Since this works with the Pascal's triangle, then this can work with combinations. If you want to know what combinations has to do with Pascal's triangle, then refer to my first video, links in the description. Anyways, what we learn from this table is that the sum of all the combinations in the nth row is equal to 2 to the power of n. I will give a better proof of this later in this video. But you are probably wondering what this has to do with power sets. Let's say I have set S, which has 3 elements. How many subsets can I get from set S? You should already know that an empty set is a subset of every set, so that's 1. The sets with a single element from set S are also subsets. The sets with 2 elements from set S are also subsets, and of course, a set with all the elements is also a subset, so that makes 8 subsets in total. But what if there was another way of counting the subsets, instead of listing all of them? How about using combinations? For example, if we want to count how many empty sets we can get from a set with 3 elements, we can just write 3 choose 0, instead of counting how many sets we have with 1 elements, we can just write 3 choose 1, instead of counting how many sets we have with 2 elements, we can just write 3 choose 2, and for a set with all the elements we can just write 3 choose 3, and with this we end up with 8. We can use the same technique with if set S had 4 elements, so here is an empty set, here is all the subsets with 1 element, here is all subsets the 2 elements, here is all the subsets with 3 elements, and finally here is the subset with all 4 elements. This makes 16 subsets in total. Now let's use combinations. For the empty set, we can write 4 choose 0, 4 subsets with 1 elements with can write 4 choose 1, for 2 elements we can write 4 choose 2, and so on. If we add them we get 16. So in general the maximum number of subsets you can get from a set is equal to the sum of combinations with n choose r, where n is the number of elements, and we already know from before that the sum of combinations where r increases from 0 to n, is equal to 2 to the power of n, so we can conclude that the max number of subsets is equal to 2 to the power of n. Therefore the cardinality of a power set of set S is 2 to the power of the cardinality of set S. Earlier in this video I said that the sum of all the combinations in the nth row is equal to 2 to the power of n. I will use a method called mathematical induction to prove this. Let's say n is equal to k. From this table, we know that there exists some values of k for which the statement is true. Now all we have to do is to prove that this statement is true when n is equal to k plus 1. On the left-hand side, I can expand the sum, and on the right-hand side, I can write 2 to the power of k times 2. Recall that I proved in the first video that k plus 1 choose r is equal to k choose r minus 1 plus k choose r. We can make use of this statement. We can expand each term except for the first one in the left-hand side, like so. You will notice that each term except for the first 2 are repeated twice, so we can shorten it, like so. As for the first 2 sum, you should note that k plus 1 choose 0 is equal to k choose 0, since they are both 1, so we can shorten that too. Now all we have to do is cancel 2 from both sides. And we are finally left with this equation, but we already know that this statement is true, because it's what we started with. Hence we have proven that the sum of combinations in the nth row is equal to 2 to the power of n. Thank you for watching. I hope you understood the topic well. Don't forget to like and subscribe.